isotropic random field. Isotropic random field produces zero net polarization. So here, for example, if you have a large-scale field, and then on top of that, B0, on top of that, there is a small-scale random field, which is statistically isotropic. So for simplicity, I made all the turbulent cells just round and with closed magnetic lines. Of course, reality isn't that simple. Then, indeed, what I just said is true. Then, if x and y are the coordinates in the plane of the sky, and z is the coordinate along the line of sight, then indeed the polarized emission depends on of magnetic field, regular magnetic field, x squared plus y squared. This is a component squared magnetic field in the plane of the sky. Meanwhile, the unpolarized emission, I, includes also the corresponding components of this small-scale magnetic field. Therefore, but the Faraday rotation is only sensitive to the magnetic field, which is a large scale, right? Because it contains the integral of the first power of magnetic field. Now, if magnetic field is anisotropic, so its cells have different sizes along a certain direction across it. Well, again, normally no cells will be of that perfect shape, and I can make a prediction for observers that sooner or later they will observe a turbulent cell with the shape of a fish. So it's my third prediction for observers. In this case, this anisotropic field will also produce polarized emission, because then, in this case, all these turbulent cells, which have systematic orientation here, because of the polarization plane is sensitive to the direction of the field, orientation of the field, this will produce polarized emission with this orientation of the E vector. Likewise here, and here, and here. So the result will be polarized emission, even though the field is purely random, and its average value is equal to 0. Then, still you can calculate, and with Dmitry Sokolov and other authors, we have made these calculations. Then, the degree of polarization depends both on the small-scale field and large-scale field. The formula looks much less attractive than the previous one, but it's okay like this. So, I decided to mention this because this fact was known since a long time ago. But only very recently, we started appreciating that this polarization coming from the anisotropy of random fields can indeed be significant enough to produce very significant, very noticeable polarization. Until very recently, people, including me, we all believe that if there is polarized emission, there must be large-scale magnetic field. The more, and there is a one-to-one correspondence, not quite. We now find quite a strong evidence that anisotropy in interstellar magnetic fields produces significant polarization. But still, this statement remains true. Whether the random field is isotropic or anisotropic, Faraday rotation measure is always sensitive only to the large-scale magnetic field. So, and this, it's not an obstacle as long as you understand the physical effect. Including it into your interpretations is always more or less straightforward. So this I want to make this comment because right now this understanding hasn't spread wide enough. So there can be various controversies, various contradictory statements related to this. So it's better to have this in mind. So let's go where we ended yesterday, here. So what have we learned and what are we learning from these observations? First, about the strength of magnetic fields. This is the histogram compiled by, in 1995, quite a long time ago, but new data don't change it very significantly, of the magnetic field strengths, total magnetic field. So now I will be talking about total and regular and random magnetic fields. So I will just write the reminder here so that we can always refer to it. So magnetic field is equal to some d naught vector plus small. So this will be called total magnetic field. This I will call large scale or the word regular. And this I will call random or small scale. I don't like the words large scale and small scale. Because what is small scale for human beings is large scale for ants, right? So when you talk about large scale and small scale, it can be very confusing, especially when people in different communities are mixed together. What is a large scale for the sun is impossibly small scale for the galaxy. So I prefer the words regular and random. These are sort of more or less objectively defined quantities. So as we can see, there are some galaxies with very weak magnetic fields, some with very strong, but typical magnetic fields range from 5 to 12, something like of the order of 10 microgauss. These are total magnetic fields. Part of this field is regular and part is random. Now discussing the details, it's reasonable, logical to start with the Milky Way. What we know about our home galaxy. This is a sort of a data you use if you want to understand the structure of the magnetic field in the Milky Way. So we are sitting within the Milky Way. Here is the sun. And these are the Faraday rotation measures of extragalactic sources. A radio source at a large distance from the Milky Way shines through the interstellar plasma, and the result is that it's polarized, if it's polarized, this polarized emission will be rotated. But from this, by observing this phenomenon, you can calculate the integral 0 to L, electron density, magnetic field along the line of sight, integrated along the line of sight. And this is the quantity which is plotted here. These positions, every dot here, every circle, is one single radio source. Altogether, there are about 500 of them. What is plotted is the value of Rm. When Rm is positive, the dot is red. This means that magnetic field is directed towards us. Blue means magnetic field directed away from us. The bigger is the circle, the larger is the value of this integral. And this diagram is presented in galactic, in polar galactic coordinates. This is the galactic equator, the plane of the Milky Way, disk. This is the galactic center. This is L, longitude equal to 0. So this is the anti-center directions. Here and here. Here is the galactic pole. So northern galactic pole and southern galactic pole. A horrible picture, isn't it? Look what a mess. We are talking about the large-scale magnetic field, and the large-scale magnetic field, if, for example, I know that the field is very well ordered, and directed on average towards me on this side, then I'm sitting, if I'm riding on a magnetic line, like this, right? So that when looking in this direction, I will see the field directed towards me. Looking here, I will see the field directed away from me. 180 degrees, right? So, I would imagine that on one side there will be a dominance of red spots, on the other of blue spots. Meanwhile, they are all mixed together. But if you spend some time, you start probably agreeing that there is a more of blue spots here and more of red spots here. So, in other words, what we have here is that definitely there is a useful signal here. There is some large-scale order. But this order comes together with very strong noise. The reasons for this noise are diverse. First, these objects themselves can have their own Faraday rotation. So part of the observed radio radiation must be attributed to the source itself. And they are, of course, uncorrelated between different sources. In addition, the galaxy itself is a turbulent medium. There must be some fluctuations. So, it's not surprising that the picture is so noisy. But what is important is that it is not enough to look just at this picture with naked eye. You need quantitative methods of analysis. Noisy signals like this cannot and must not be analyzed without rigorous mathematical methods. The statement is trivial. This statement, in fact, was first made by Friedrich Gauss, who introduced the method of least squares exactly for this reason. But people now tend to forget what they have heard from Gauss. People, the danger here, and I will discuss it further, in this area, especially about the Milky Way, systematically people try to extract, to make conclusions about the structure of the magnetic field, just by inspection of such fields. Very often coming to absolutely unacceptable conclusions. And I will talk about this just because the problem has become quite widespread. And there are quite a number of papers which can really very strongly mislead. So, I was involved in analyzing exactly this map, together with Dmitry Shukurov and Peter Frick from Perm and Rodion Stepanov. What we did, so what? You have here a noisy signal. You want to filter out noise. How to do that? There are several ways to do it. It's either Fourier filtering. In this case, this would be filtering in the space of using expansion in spherical harmonics. But perhaps even more conveniently, you can apply wavelet transform and extract signal at a certain scale. This is what we have done. And this is the Fourier wavelet transform. So what we did, we performed wavelet transform with the simplest wavelet, Mexican hat, and then plotted the spectrum, wavelet spectrum. And this is the image at the scale 76 degrees, where the power is maximum. So this scale contributes most of the power in this map. And here you clearly see this red spot and blue spot. Moreover, you clearly see that the picture is symmetric with respect to galactic. So, all the other things are just small scale perturbations. Most of them are local, just because they come. Remember, on the map of the Milky Way, I mentioned the North Polar Spur, this nearby supernova remnant. It produces this red spots and these blue spots. They are produced most probably by this North Polar Spur. They are local. So this is the most convincing, to my knowledge, evidence of the quadrupolar symmetry of the galactic magnetic field. The galactic equator is here, running just in the middle of this frame. So here we will probe the horizontal magnetic field, and it's clear that the horizontal magnetic field is an even function of the distance above and below, of the distance from the galactic. So the first conclusion from this experience, from this data, is that first, the data are noisy and need careful treatment, and second, still, we can be quite confident that what we see does have a large-scale component, and this component has an even symmetry with respect to galactic field. So, quasi-spherical objects, or the sun of the Earth, they are characterized most often not by pure, but still predominant dipolar symmetry. Why flat objects like accretion disks, perhaps, and galaxies have even symmetry? This comes from a simple fact, from the thinness of the disk. Just to make this argument simple, let's consider magnetic decay time of these two configurations. In the dipole, the poloidal field is that of the dipole structure, And the toroidal magnetic field changes sign across the equation. In the quadrupolar magnetic field, again we have here 4 poles for the colloidal field, and the toroidal field is an even function of the distance from the midplane. What will be the decay time of this structure? This will be equal to h. H is the distance between these 2 belts of field, squared, divided by eta. Likewise here, but here a factor of 2. Because here the distance, imagine now that I have squashed this into a disk as thin as this. It's clear that this additional reversal in the midplane will make this configuration to decay faster. If it decays faster, it is harder to excite. This is basically the reason why thin disks prefer quadrupolars. In spherical object where these 2 belts can be widely separated, this difference becomes negligible. This difference becomes absolutely unimportant because it's spherical objects. But in flat objects where these 2 belts are strongly pushed towards each other, this difference is significant. Of course, there's a qualitative sort of an explanation, it's an interpretation of solutions. I can solve equations to show that in a thin disk, quadrupolar modes will be preferred. Now, this is again the data of RN, prioritization measures, but now of pulsars. And this is the view of our galaxy from above, face on view of our galaxy. Altogether, we now know the prioritization measures of about a few hundred pulsars, 400 something pulsars. They are scattered all around the galaxy. For most of them, we have at least some vague some idea of their distance. They are very useful instrument to find out what is the structure of magnetic field of the Milky Way. So the Sun is here. This is the galactic center, and these are these dashed lines. They show the structure, the spiral arms of the Milky Way. Here is the Sun. The symbols are crosses of these 2 shapes. Show magnetic field which is directed away from us, right, towards us, and the circles and squares show the magnetic field which is directed away from us. Let's look at this picture. So many circles here. Here, circles and squares are just mixed like mad. Again, the same picture. Very noisy picture. Even though what is plotted here is the integral, and usually the errors reduce when you integrate. Nevertheless, the noise remains to be very strong. Again, the same conclusion as here. Be careful when analyzing this data. But this is exactly where I will start criticizing, knowing that it's better to criticize people, especially when they are not here. But the situation is more or less extreme, because now people start interpreting such maps by almost by naked eye. They make far-reaching conclusions, and then people start referring to these papers, taking this as an established fact. For example, what is remarkable, it's here in this galaxy, in our galaxy, in 1980s, one of the first analyses of this sort was done by Phil Kronberg in Canada. It was a very good paper, very good analysis, and he showed that the magnetic field reverses somewhere here. The direction of the magnetic field near the Sun is, the field is directed, if I remember correctly, from left to right, and here in this arm, it's directed from right to left. A very non-trivial feature. And now, people started looking for further reversals. Is there only one reversal of magnetic field, or are there more? And then, look at this integral. Imagine now that this B parallel isn't sign constant. So that along the distance, this is the distance away from the Sun, and this is Rn, this integral. Imagine that magnetic field behaves like this. Positive and then becomes negative. This is B. It's clear that the integral first will grow, and here the contributions to the integral will become negative in the integral will start decreasing, right? Fantastic. How simple. And here we have sources. We can choose a certain direction. There are many sources here. We know distances to them. Just plot this RM as a function of distance. If there will be such a change in the slope, you have detected a reversal. And this one has been done. So the distance along a different certain direction, and this is RMs of pulsars which are along this direction. Look at how fantastic. How many reversals? Everything reverses. Almost everywhere. The result is this picture with 1, 2, 3, 4, 5 reversals. It's totally fine. Look here. Where are the errors? Where are the errors? No, the errors are very small. Because when you integrate, now, this B consists of two parts, right? B is equal to B parallel, B not parallel, plus the turbulent field, parallel. Clear, when you integrate, the contribution of the random part decreases. And you can know the value of the integral along the given direction with very high errors. So these errors of RMs themselves are very small. But we are not interested in the value of RM in a given direction. We are interested in the contribution of this part of the field in this direction. Therefore, we should attach to each of these points an uncertainty resulting from the turbulent field. You have to filter out the noise. Therefore, to interpret this picture, you should plot on top of it the value of the sigma Rm, the standard deviation of Faraday rotation measure of this integral, which arises from the turbulent magnetic field, B small, which can be calculated. We calculated it yesterday. Here is the formula. So I took one of the panels from this paper. I think it was this one or what. They will be more than, right? And now, this first, look at this number, 250 radians per square meter. The magnitude of the signal is comparable to that, 500 radians per square meter. Well, a bit larger here, but in addition, this grows to the square root of L, of distance. The farther you integrate, the wider, because of the random walk, the two polarization angles will diverge, the larger will be the contribution of the turbulent field. So now, I have plotted this sigma Rm at a distance of 2 kiloparsecs. At 4 kiloparsecs, it's twice as large. Not root of 2 large. Do you see the signal? Do you see the increase? With an errors, it's just a constant. Let's just see it. Here, there is an evidence of reversal. Do you see it? No longer. No longer. Underestimated errors. Underestimated errors. I wonder who was the referee of this. But whoever was the referee, the paper has been published, and now it has a high number of citations. People accept these results as the final truth, with elementary mistakes. So this is the only reason why I decided to present it to you. So, except for various reasons of human nature rather than scientific nature, this area of the interpretation of magnetic field observations in the Milky Way has suffered more than other areas. So be careful. Don't accept statements, also from me, uncritically. Try to assess is it reliable or not. Continue, right? What else I want to say? So this diagram presents what I think we know more or less confidently about the magnetic field in the Milky Way. First, the total magnetic field gradually decreases with distance from galactic center. Here in the center, the situation is always in the central parts of anything is more complicated. It's a world of its own. So we don't extend it, not me, Ehrenberg using. She didn't extend it quite wisely toward the center. So closer to the center of the galaxy, at a distance of a few kiloparsecs, magnetic field dot field is about 10 microgauss strong, and then its quasi-exponentially decreases with distance, decreasing down to what, 1, 2, 3, well, about 5 microgauss at the edge of the galaxy. These points represent a large-scale magnetic field. It is so it's clear that the turbulent magnetic fields dominate everywhere, and there is definitely one reversal in the inner galaxy. So magnetic field, the direction of the magnetic field, large-scale magnetic field, here and here are different. At a distance of 500 parsecs, half a kiloparsec distance, towards the center of the galaxy, the magnetic field definitely reverses. Whether or not there is another reversal, it's not clear. It's not also clear if there is any, if there are any reversal sites. But putting here 5 or 7 reversals, which right now, without careful analysis, is just mad. So this diagram, this simple diagram, presents what we know more or less confidently in this area. Now I will make a review of observational pictures of external galaxies. And this selection, of course, will be incomplete. I don't even attempt at making a complete review of observations. Instead, what I have done, I have selected those observational facts which, to my mind, help us to understand the nature, the origin of these magnetic fields. And in particular, it's not because I made this selection. I will argue that most, if not all these facts, do argue in favor of dynamism. They do strongly suggest that these magnetic fields cannot be just frozen in primordial magnetic fields, a relic from pre-galactic past. I should say that if there were arguments, observational arguments against this viewpoint, I would present it here. So, in this sense, there was no bias. Simply there are no such observational facts. This is the message I want to give. Look at this example. This galaxy is called NG36946. And here there are two images. The black and white image is the distribution of ionized gas in this galaxy. So you see here the spiral arms, quite strong spiral arms. One spiral arm, another one. It's quite complicated spiral pattern. On top of that, the contours show the total and polarized intensity in this galaxy. So here the contours are the tracer of the magnitude of the total magnetic field. Well, some mess here, but it's more or less filled. Well, everywhere there is some magnetic field. Fine. Now let's look here. This is polarized intensity. So this is the tracer of the large-scale magnetic field. And remembering my comment, perhaps also some anisotropic magnetic field. Okay, now you see quite nicely spiral arms. Fantastic. So the large-scale field is stronger, and the anisotropic magnetic field is stronger within the outer spectrum. Fine. Everything is fine until you look closer into this picture. Look at this arm. How it is related to that gas. Gosh, it's exactly between the gaseous spiral arms. So the magnetic field, large-scale magnetic field, is stronger where gas density is small. Meanwhile, if magnetic field is frozen into a gas, imagine that you have a cloud of gas whose density is rho and whose magnetic field is d. Imagine that it's compressed or expands. Then there will be two, and its radius is r. Then, as if magnetic field is frozen into the gas, then the magnetic flux should be constant. dr squared must be constant. The flux through this cloud, through this region, must be constant. Mass is also conserved, right? So rho r cubed must also be constant. From this I immediately get the unique one-to-one relation between density and magnetic field. For spherically symmetric evolution, B will be proportional to rho to the power 2/3. I just eliminate R between them. Or, it's another way to say, I think Kandor was writing this equation, a way to write out the Alvin's theorem is to say that d by dt over B over rho is a constant. It is 0. So, B and rho are connected to each other. This is what it means a frozen in magnetic field. So, you immediately expect that where rho is larger, their magnetic field will be stronger. Right? For a frozen magnetic field. Why? Why this magnetic field is stronger where the gas density is minimal? And this is also true in this arm, and in this arm, and in this arm. To very fine detail, the large-scale magnetic field avoids staying where it is supposed to stay if it was frozen in. Obviously, when it was Reiner's back observations, when he derived these maps, we tried everything to explain this. For example, additional ordering of magnetic field here. We tried everything thinkable. Nothing works. It's indeed true. There is an additional component of the large-scale magnetic field which sits where density is minimal. So this is direct evidence of the fact that this large-scale magnetic field is not frozen into the gas. It is not. Look at this picture which I already showed, right? M51. What is important now for me is that magnetic field in the disk and in the halo have different configurations. Very different configurations. Now imagine that this magnetic field is a primordial field. This means that I have some initial magnetic field which was then twisted by differential rotation.
Sorry,
Yes?
Couldn't be some kind of buoyancy that is driven the magnetic field lines away from the plasma? If you get boiling unstable, they should get away to less density, right?
If it's frozen in, it's frozen in, right? Magnetic field cannot move without plasma. What can happen is that, for example, it's like buoyant instability. When there's a loop, then the gas moves down the line, and therefore there is, but then magnetic field becomes even more buoyant and goes God knows where. Why should it stop somewhere? And in addition, the scales involved, right? So this buoyancy, right, it will work only the typical velocities will be what? Sort of Allen speed, right? Or free fall speed. Of the order of 10, 20 kilometers per second. The distances here are sort of 4 or 5 kiloparsecs. And in addition, all this rotates. This all rotates differentially. So this pattern of spiral arms, it's a wave. It rotates as a solid body. The gas itself rotates differentially. Why? They are so perfectly phased. If magnetic field is frozen into the gas, it must follow the differentially rotating gas. Because these arms are just waves, density waves.
Is that plot of the whole magnetic field?
Sorry?
Is that plot of the magnitude of the magnetic field, or just its azimuthal direction?
No, these dashes, they show the polarization plane, and the length of the dashes is proportional to the degree of polarization. And these are the contours of roughly B squared. Contours of B squared, large scale B squared. So this is the point. If it's frozen into the gas, it must rotate differentially. The spiral pattern rotates as a solid body. These are waves. How come? How come They are so perfectly organized with respect to each other.
Since they are different, they are really,
Yes, 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 exactly, exactly,
and
exactly.
the magnetic energy of I don't know, the field line is increasing, right?
Increasing, yes, yes. And what? Still, there will be exactly this. This will rotate faster, this will rotate slower. Why all of a sudden is it a unique moment in the history of this galaxy where 1, 2, 3, 4 spiral arms happen to be exactly between the gas arms and having exactly the same pitch angle. If magnetic field is frozen to the gas, the blue contours must rotate differentially, and the gray scales must rotate as a solid body. Yes?
How do you know that the frozen law applies to these?
I don't know. I want to decide.
Because there are lots of instabilities between the diffusion of magnetic field.
Absolutely. Exactly. I agree with you completely. But even if this conclusion seems to be natural to you and me, there is a significant number of people who disagree. And they can continue saying that there is a primordial magnetic field twisted by differential rotation, don't need any dynamics. I agree with you completely, yes. This is a conclusion which is, to me, seems unavoidable. But on the other hand, it's very difficult to be so confident in various things. It's always useful to check again your arguments. This is what I'm going to do. Conde, we had something to say.
So, I thought your argument about pitch angles in any of these things is a much simpler argument.
We shall come to this. But here, it's a very spectacular thing where magnetic field strength is just not proportional to gas density, as it must be in the case of frozen magnetic field. And whatever you do, you cannot explain it with reasonable physics. Whatever you try. So here, now imagine that you have a primordial magnetic field. You have a galactic disk. It captures, when formed, some large-scale magnetic field which extends to infinity. Then it rotates, and it will twist magnetic field to some spiral configuration, like this, which resembles, quite reasonably, the spiral configuration we have here. Do you need anything more? Let's forget about turbulent diffusivity and all such stuff. Fine. How then are you going to explain the fact that in the hell of this galaxy, the field has entirely different configuration than this? Of course, I can always invert the induction equation in time. I can take this as an initial condition. I can step back in time and find the initial magnetic field which will produce this configuration for a given velocity. But I bet the result will be absolutely bizarre. Where from such a bizarre initial field might come to produce this configuration now? It's just unthinkable. It's so artificial. So just the very fact that this galaxy has so different configurations of the magnetic field in its different parts indicates that there is something non-trivial must be happening. It's not just passive magnetic field twisted with differential rotation. I'm spending much time on this, trying to demonstrate the need for the dynamo action. For a simple reason. In the case of the sun, or stars, planets, and the Earth, the need for the dynamo is uncontestable. Everybody agrees with that. Because, in the case of the Earth, the first argument was that the ohmic decay time is very short. It was, what, a few tens of thousands years, right? So, no way. But then when reversals of magnitude of the Earth were discovered, it made the opinion just absolutely firm, cast in bronze. If it changes the direction, time variation directly shows you that magnetic field must be created all the time, reproduced all the time. With the sun, the activity cycle directly tells you that there is something non-trivial happening, that this cannot be just passive frozen magnetic field. In the case of galaxies, here the galaxies are very easy prey for primordial models. For example, well, because the time scales involved are millions and hundreds of billions of years. Therefore, You can only decide what is the origin and nature of this magnetic field from their shapes, from their forms, not from their time of evolution. You don't know how it evolves in time. And this is what makes these arguments in favor or against dynamo theory or any other theory significantly more complicated than in the case of stars and planets. So, altogether, in spiral galaxies, magnetic fields are total magnetic fields, have the order of magnitude of about the strength of the order of 10 microvolts. And the ratio, and this field is dominated by random magnetic fields. The ratio of the random to regular energy densities is about 3. Well, 3, 5, less than 10, larger than 1. And roughly there is competition with turbulent energy. For the turbulent field, roughly, or if you wish, Alvan's speed is equal to turbulent speed. We may interpret it that way. Generally, the field has quadrupolar parity. This fact is non-trivial. It has been only established more or less firmly in the case of Milky Way. In no other case, in no other galaxy, we have a possibility to confirm or disprove it. So this statement, even though it is by most authors in most papers, it is presented as a very firmly established fact, we still should be careful. It has been firmly established for the Milky Way, not for other galaxies. It is impossible to compare it to other galaxies. This is an old simulation of Axel. This is the solution of mean field dynamic equations, and the disk did it with Carl Johan Dorner, and I took it from our review of 1906. So this evolution is an example of evolution of magnetic field in a mean field disk dynamo. These are the face-on views, this is the edge-on view. This is how it happens. Gradually, you get magnetic lines which form these spirals, and in the meridional plane, they form a quadrupolar path. Again, with pictures like this. What happens? Magnetic lines should be all closed, right? What? Is the wrong solution? Is divergence is different from 0? Of course not. Of course not. What is shown here is the horizontal magnetic field. And the divergence of the horizontal magnetic field alone doesn't need to be equal to 0. There is also dBz by dz. Again, I'm mentioning this trivial fact for a simple reason. Just very recently I was referring a paper where, again, when analyzing data like this, people were arguing that all analysis, which involved only horizontal field, because the vertical magnetic field here on average is negative, that all previous analyses are wrong, because the fixed magnetic fields, Br and B5, have divergence different from 0. Therefore, everything needs to be reconsidered. Just mistake. Of course, if you have even a thin disk, and you have the divergence of magnetic field must be equal to 0. So 1 over R, d by dr, r dr, plus 1 over r, dB5 by d5. I hope I remember the divergence of cylindrical coordinates correctly. dBz by dz must be equal to 0. On average, bz is equal to 0. Can we neglect this term? No, we cannot. Because the disk is thin, therefore, d by dz can be large. The order of magnitude of this term is dz over h. The order of magnitude of this term is br over r. Bz is smaller than br, but h is smaller than r. So these two terms can be comparable. And then it's not surprising that the divergence of the horizontal field alone differs from 0. It's just equal to minus this. This is sort of an elementary business. But when you have to refer a paper where people make this mistake, having done this analysis, then now start talking about the non-zero divergence, it makes you worried about the future of astronomy. Right? So the magnetic patterns in all galaxies known to us are all spiral. Magnetic field never forms a closed circular toroidal loops. It's always a spiral, like we had here. It's always a spiral with a typical pitch angle between 10 and 30 degrees. So, meanwhile, the streamlines of the gas are practically closed. These are almost perfect circles. And therefore, magnetic fields are not aligned with gas streamlines. Again, that indicates that magnetic field will not necessarily be frozen. This is the observational data for a selection of galaxies. The P, pitch angle, is the arctan of Br over B phi. If I have if this is my galaxy, this circumference, the electric center is here. If this is magnetic line, then this angle is known as the magnetic pitch angle. The angle between the magnetic line and local circumference. It's minus P. It changes in the inner galaxies. It can be, this angle can be rather large, so magnetic line can go quickly in. But as you move out, the pitch angle systematically decreases. So the spiral becomes more tightly wound away from the galactic center. So let me try to make a sketch. So if this is like that, so it is here, it is tightly wound, but then it goes faster inside. This sort of behavior. And this agrees very well. I will explain why when we shall be solving dynamo equations. Agrees perfectly well with the dynamo theory. For example, this is this diagram shows magnetic pitch angles in M31, the Andromeda Nebula, the nearby galaxy. These points with error bars, these are observed pitch angles. Now it's P itself, so it's negative, right? So because the large is the radius, the small is the magnitude of the pitch angle, like here. The small is the magnitude of the pitch angle. And these curves and dots represent different models. Of course, there is always a range of models. I should say that the most detailed models here are those which show the worst agreement. Dots show the model which is the most complicated. And these curves which agree better show the very crude order of magnetic estimates. So I cannot claim that the agreement is perfect and there is nothing else to do. It's not perfect. But at least what we have is the trend, for example, is correct. The order of magnitude of these quantities is also correct. So this is quite, to me, even though the agreement is far from being perfect, still to me it's an achievement of the dynamo theory. It does agree, at least roughly, with observations. Complicated spiral structures like magnetic arms, different reverse of magnetic field, they're quite widespread. They're quite widespread. By the way, with reversals in the Milky Way, there's another puzzling thing about it. At least one reversal is very confidently has been confidently observed in the Milky Way, despite quite a lot of effort. Nothing of that sort has ever been observed in any other galaxy. So, anti-Copernican view, Milky Way all of a sudden becomes again unique. It's different from all other galaxies. It's very unpleasant. It shouldn't be like that. So this reversal is a sort of headache. It's not impossible to explain these reversals. You know, somehow you can construct models which do indeed show that such reversals would have a longer lifetime in Milky Way than in, say, Andromeda Nebula or M51. But still, its station is unsatisfactory. The origin of these reversals and their significance isn't quite clear. And there is a widespread misconception. Very often, almost in, say, 95% of cases, people take the results obtained either from theories or from observations for the solar vicinity of the Milky Way, and then start believing that they apply to all galaxies. For example, the magnetic field near the Milky Way, the large-scale magnetic field, has the strength of 1, 2 microgauss. But if I plot magnetic field B naught, and there is the sun, we know that we live near the reversal. The sun is somewhere here. Of course, magnetic field will be weaker here than elsewhere. So this is not the strength of magnetic field near the sun. Is not a typical field, strength of the field in spiral galaxies. I would say that typically the large-scale magnetic field in spiral galaxies is of the order of 5 microgauss, factor of 2 or 3 stronger than this. Another misconception, when we shall be discussing the dynamo models for magnetic field, we shall derive the growth rate, the E-folding time of the large-scale magnetic field near the sun. This E-folding time will be of the order of what? 5 times 10 to the 8th years or 10 to the 9th years. Fairly low. And then you can find a few hundreds of papers which conclude, so the dynamo action is so slow, the galaxies haven't lived enough to have magnetic field amplified to observe values. But these are not typical values in the world of galaxies. For example, in the same Milky Way, where the rotation rate, the velocity shear rate, rapidly increases inside, so if I plot here R, and the rotational shear rate, R d omega by dr, by modulus, it behaves like this. The sun is somewhere here. So even if you move just 5 parsec inside, it increases by a factor of 2, which will result in much shorter time scale. Other galaxies rotate much faster than the sun, than the Milky Way. In the same galaxy M51, the corresponding E-folding time is of the order of 10 to the 8th years, and definitely not 10 to the 9th. So again, there are literally hundreds of papers whose starting point is a complete misconception, based on the assumption that the values obtained for the Milky Way apply to all galaxies and all regions in all galaxies. This is wrong. What else? Galaxy clusters. Just a picture to remind the coma cluster, this central part of the coma cluster containing about 1,000 galaxies. And this is a similar image of the same cluster, but now in X-rays. So this color, shown with color, is the distribution of very hot gas. And here, if this distribution is more or less homogeneous, and until when people only had optical pictures like this, they were quite confident that this cluster, especially this cluster, coma cluster, it's a very well studied cluster, rich nearby cluster, studied to very fine detail. People were absolutely confident that this quasi-spherical system completely relaxed gravitation until observations of this type started emerging. Look at this. Look at this block. With hindsight, you will see some enhancement of galaxies in this region. This cluster is in fact in the process of merging. This clump merges with this bigger part of this cluster. And these observations have completely changed our view of the clusters. Let's see what we know about magnetic fields in the clusters. It's the same cluster, but now observed at radio waves. This is synchronous emission. And we see that indeed, let's look again here. So we have this roughly spherical distribution of gas in galaxies here. And here there's another block of gas. Yes. And all contain magnetic fields. It's very patchy. It's very patchy. But still, there is a clearly magnetic field. Now, this synchronous emission requires two things to be produced. Magnetic field and cosmic rays. the main problem with this stuff, such radio halos, such synchronous emitting regions, are called radio halos of clusters. They are relatively rare. Only about 10% of clusters possess emit detectable signal emission. So, and until a certain time, it wasn't clear if magnetic fields are the typical constituent of clusters. But then, more convincing evidence comes from observation of Faraday rotation. Here, we shall return back to the signal emission, having discussed this picture. What is plotted here is from the paper of Clark and Phil Kronberg, and I don't remember who was the third author. What is plotted here are the Faraday rotation measures of background sources seen through the clusters. So what you do, you have a cluster of galaxies somewhere here, and you observe a radio source, polarized radio source, which is projected on the cluster. And you try to observe as many sources as possible at different distances, projected distances, from the cluster center. And then you plot the resulting Faraday rotation measure, this integral. As a function of distance, projected distance, to the cluster center impact parameter. White points show the sources which are projected on the cluster. Black dots show the sources in the control center, the sources which are not projected on any cluster, any known cluster. Now look at this. There's a clear line here. Rm for these black dots is clearly fluctuates around 0, right? But white dots, open circles, clearly and widely deviate from 0. And the closer you are to the center, the stronger is this deviation. So this is the evidence. How many clusters? 16 galaxy clusters, right? And out of 16 galaxy clusters, there is none where the white sources, white points, which would cluster around 0. All these 16 clusters produce random, but significant Faraday rotation. So how come then that synchrotron emission is produced in so few clusters, just 10%? Meanwhile, Faraday rotation is produced in most clusters. The present opinion is that the problem is that it's difficult to maintain a population of relativistic electrons in the intergalactic plasma. So magnetic field is there in all the clusters. But not all the clusters contain relativistic electrons. So this is the current viewpoint. And it's a reasonable viewpoint, because relativistic particles, they rapidly lose their energy. Cosmic rays need always to be regenerated, reaccelerated, because at least for the losses to the synchrotron emission, they emit synchrotron. This reduces their energy very quickly. Therefore, you need to accelerate electrons just everywhere throughout the cluster. It's one of the ideas. And it's a hard thing to do. It's a difficult thing to do. Meanwhile, magnetic field, if it has been created once, it's not easy. It's hard to generate magnetic field. But by the same token, it's hard to get rid of it as soon as it has been generated. So explaining why magnetic fields can be widespread in such clusters is easier than explaining why cosmic ray electrons can be widespread in clusters. So the present opinion is that most clusters do contain magnetic fields, but a minority of them contain relativistic electrons. Therefore, synchrotron emission is observed from a minority of clusters, but Faraday rotation is observed in most of them. So this is an example of Faraday rotation in another case. These are radial lobe of a large galaxy, radial galaxy, which sits in the center of a rich cluster of galaxies. Then these lobes, this is the end of a powerful jet, which starts at the galactic center somewhere here and ends here. So this volume, presumably, is filled with relativistic plasma, electron-positive plasma. So it does emit polarized emission. And you can see that this emission is polarized, and you can detect further rotation here. It's not quite clear where this further rotation originates. Part of it can originate in a shell of this region made of thermal gas, which was produced when the jet was moving through the medium. But still, at least part of it should be produced in the along the line of sight, within the cluster itself. So such estimates suggest that the magnetic field strength here is about 2 or 10 microgauss, and its scale is about 20 or 30 kiloclusters. And this is quite an impressive thing. We are talking about clusters which contain thousands of galaxies. It's a huge object. Meanwhile, the field strength is comparable to the strength of the field within a spiral galaxy. And the scale of this field is comparable to the size of the galaxy. Again, if magnetic field was frozen into the galaxy, for example, if it scales, let's imagine that magnetic field of the galaxy is expelled from the spiral galaxy into intergalactic space, right? 10 microgauss, the density within the galaxy is, say, 1 particle per cubic centimeter. The gas density within the cluster is 10 to the minus 3 particles per cubic centimeter. If the expansion was spherically symmetric, the magnetic field within the cluster will be equal to magnetic field within the galaxy times rho cluster over rho in the galaxy to the power 2/3. So 10 microgauss, and here I will have what? The ratio will be 10 to the power 3, right? To the power 2/3 times 10 to the minus 2, 0.1 microgauss. So this field is factor of 100 stronger than one might expect from just expansion of the magnetized field from galaxies. So it is a very strong field. It is a very strong, non-trivial magnetic field. Here, let's look again at this diagram. So let's suppose that magnetic field is of the order of 2 microgauss, the lower end of the range. The size of the region, which is magnetized, this region, is 500 kiloparsecs. We know. You can just know. The gas density we also know, because this gas emits thermal X-rays, and we know it is dense, 10 to the minus 3. What value of Rm it will produce? Just multiply everything, you will get 1,000. 1,000 radians per square meter. What we observe? Oh dear. Where is 1,000? There is no 1,000. 100 is the typical Rm. Why? What's wrong? And what is wrong here is that when multiplying these 3 numbers, I assume that this magnetic field is regular. And if it doesn't work only because the magnetic field is random. And then, this means that what we observe here is this, again, the same sigma Rm, the standard deviation of phylogration measure in a random medium. Then, to calculate the expected Rm, in fact, we should use again the formula we derived before. Or we can perhaps write this formula in such a different way. So, sigma Rm will be equal to this typical value of Rm, this 1,000. Rm naught, divided by root of the number of turbulent cells along the line of sight. Right? Number of turbulent cells divided by the line of sight. I want to reduce it by a factor of 10, so n is the order of 100. So the size of the region is 500 kiloparsecs. There are 100 cells. The scale of the field must be of the order of 10 kiloparsecs. So you immediately come to the conclusion that what we have in the clusters is a random magnetic field of the strength of a couple microgauss, whose scale is comparable to the scale of the galaxies. Then all the ends meet, and we have more or less acceptable general picture. There are several ways to estimate magnetic fields in galaxy clusters. This is a table I copied from a review, more or less recent review, 7 years old now, of Carrilli and Taylor in annual reviews. So, from the intensity of circular emission, assuming equipartition viscosity of electrons, the strength of the magnetic field follows as about a fraction of microgauss. So for the 1 microgauss, perhaps half. The Faraday rotation of sources within the clusters predict magnetic field of the strength of the order of 10 microgauss with a cell size of 10 parsecs. Background sources give a slightly bigger magnetic fields with the same cell size. I would think that this 41010 is perhaps towards the upper end. This seems to be a little bit too strong. There are additional constraints on magnetic field which all give you results something of the order of 1 or a few micrograms. So you can accept as more or less firmly established observational fact that magnetic fields in galaxy clusters have the typical strength of a few microgauss and a typical scale of the order of 10 kiloparsecs. Now, very briefly on accretion disks. I just couldn't avoid mentioning them, they're beautiful systems, but I had no opportunity to discuss them in detail. It's a world of its own. Yes?
Before we leave that, I mean, we're all intrigued. Where does this field come from in the clusters? Galaxy clusters.
Wednesday and Wednesday. Oh no, Wednesday, maybe Thursday. Yes, we shall be discussing the origin.
That's a quick answer, because small scale.
During the merger, obviously there will be some turbulence generated. In such a violent event, there will be all sorts of turbulent motions. Then, creating seed fields isn't a very big problem. You will always have a seed field. And then you can argue that even during this merger, you will have decaying turbulence. The merger will leave decaying turbulence behind it. And the turbulence decays slowly, right? Turbulence decays as a power law. So there is enough time to produce noticeable magnetic field. I will argue. It's not a completely firmly established fact. I cannot say that it's sort of...
Because I mean, you pointed out that I mean, we were talking about sort of 10 to the 8, 10 to the 9 years the growth rate for galaxies.
In the galaxies, yes.
Naturally, one would assume from the beginning. I mean, I don't just...
But there, yeah, we shall see. But it's an interesting thing because but this will be a fluctuation dynamo. The clusters don't rotate as a whole, and fluctuation dynamo is fast. The typical time of the fluctuation dynamo is just 1 kinematic time. So this is how I will try to squeeze away to get away alive from this problem. So, but I cannot say that these objects are. Our knowledge is complete. For example, this gas is collisionless. And I will be discussing application of MHD. So, if you are really very skeptical and critical, at that point you may stop listening. It's a problem. Alex Shibachigin is now working on this, on the plasma effects and then collisionless plasmas, what happens with magnetic fields in collisionless plasmas. But this is an open question. It's a collisionless gas, which makes it interesting, right? Again, a new creature in the UC. Now we have collisionless plasma. It's turbulent magnetic field. Can I continue? So, accretion disks. They are very widespread. They occur, for example, in binary systems around massive black holes, around compact stars, young stars. The accretion disks arise just because everywhere there is angular momentum. As soon as everywhere there is gravity and angular momentum. If there is gravity, it starts dragging matter on it, a gravitating center. And as soon as this matter has angular momentum, it will never fall on the gravitating center in a spherical symmetric manner. It will always form a disk, because it will need to get rid of the angular momentum before falling down. So, accretion disks are very widespread, and since usually the density of the gas which falls down is relatively small in comparison with the central object. Most of the gas, most of the gravitational potential, gravitational force, is produced by the central object. This means that the rotation will be near Equiparian, practically Equiparian. Only the pressure in the gas can produce slight deviations from Equiparian. They are very thin. Why they are very thin? Because the gas is relatively cold, and because it rotates faster. The most important, the first context in which these accretion disks attracted attention in this area from HD is that they drive fantastically energetic outflows. What drives these outflows is still unknown. They are fantastically well collimated, these outflows. They are called jets. They have been first observed around active galaxies through their singular emission, and then later they were observed in young stars. So it's again a widespread phenomenon. These accretion disks, they drive very narrowly collimated and very powerful outflows, jets. I will show you pictures first, and then we shall discuss the parameters. Nobody knows what drives it, exactly what drives it, despite enormous effort of a large number, perhaps a few hundred in this community, of very clever and very well-educated people. Their progress is very slow. We still don't know what drives the outflows and what exactly. There are, of course, theories, there are various models, but nothing is entirely convincing. And especially what collimates these outflows. It's really absolutely enigmatic, spectacular and enigmatic objects. So these are a few pictures, right? So this is just artist's impression of how it happens. You have here a compact star in the center. You have here a normal star. And the gravitational pull of the companion drives matter through Roche laws, Lagrange points, and then it comes to an accretion disk because there is a mutual rotation, mutual angular momentum. These are the observations of a young star in the Milky Way, HH30. This is the disk here. What you see here, the dark shade here is the disk itself. And this light, these bright regions, is in fact the light of the star reflected from the surface of the disk. So it's like this. The star is somewhere here, the disk has this shape, and you cannot see the star because it's behind this side of the disk. But its light is reflected from this surface, so you see the reflected light reflected on the surface of the disk. So this is the disk surface, the farthest from you, shining the reflected light. So this is the structure. It's a sketch which shows this structure. So this is the disk whose thickness grows with distance for the same reason. Gravity, temperature decreases only slowly, pressure decreases only slowly in radius, gravity decreases rapidly, so in hydrostatic equilibrium the thickness will increase. So this part, remote part, reflects the stellar light. And look at this jet. Look at this. Look how narrow and straight is this jet. It starts from the star. The star has almost negligible size in this image. Now, this is even more spectacular case of extragalactic jet. Now here, this is a giant elliptical galaxy, and this is the zoom, it's the very center. You can see here, this one is Hubble, I think, Space Telescope. You can see here the central object, presumably black hole of the 100 million solar masses. This is the accretion disk. And then look at these jets, which start here and extend over absolutely mind-boggling distances. So this is the whole galaxy. The size of this galaxy is, say, 30 kiloparsecs. 30 kiloparsecs. 30 kiloparsecs is what? It's 100,000 light years. 100,000 light years. And then 1, 2, 3. Each jet is 3 times longer than that. So it's the same as coming to your yard with a hose pipe, right? You switch on water in the tap, and you see with amazement that the jet of water from a hose pipe doesn't disperse, but reaches the moon, and hits the moon, remaining collimated. It's a phenomenon of this. It just cannot happen. It's just impossible. Something driven by the accretion disk, which cannot be even visible in this scale. You need to zoom enormously. So this is 400 light years. The size of this image is 88,000 light years. Something which is small, even in this image, drives something which is large, even in this image. It cannot be true, but it is true. These are absolutely fantastic. Absolutely fantastic objects. We spent with Axel quite a time, right, trying to work on this, without very much success, right? But these are fantastic things. This is another example. Again, this small spot isn't a black hole. It is the whole galaxy. And from the very center of this galaxy, from the small black hole whose horizon has the radius of astronomical units, I guess, right? For this size of black hole, drives, look at this jet, absolutely straight, perfectly coordinated. The opening angles of these jets are of the order of 2 or 3 degrees. 2 or 3 degrees opening angle over a distance by orders of magnitude larger than the size of the galaxies. And then, sooner or later, of course, the jet ends, and when it ends, it produces these powerful radial lobes, clouds of relativistic plasma. It is believed that these jets most probably are filled with relativistic plasma. They produce very strong synchrotron emission, but Faraday rotation is negligible. This means that thermal electron density is very small. So they probably are filled with relativistic plasma. Amazing, absolutely amazing. I will not be talking about this just because I can describe them at the level of zoology. I can describe them in length, you know, but you don't know what's their origin for certain. There are models, very interesting models, very beautiful models. That's it. I think I'm prepared to start the next section, but probably not, right?
Maybe there's questions.
Everybody's tired. Oh, what?
Yeah, maybe you use the time to ask questions if there are any.
Probably better to start questions, because otherwise everybody will start hating me even more than now.
So about the clusters, you said the reason for the absence of radio emission from most clusters which do have X-ray emission is the lack of highly energetic cosmic ray electrons, rather than the absence of magnetic fields.
Yes.
Is there any other argument which could support this? I mean, is the level of turbulence the same, for example?
I don't know.
Because I was under the impression that there could indeed be a lack of magnetic field. I mean, we are talking about a small-scale dynamo. That was Chris's question. And your argument was magnetic field is hard to generate, but then you also said a magnetic field in a cluster is a small-scale dynamo. That one is easy to generate, and by the same token, that is easy to destroy.
No, it's hard to generate for those who don't know the dynamo theory. I should introduce a qualification to my statement.
But not for us then.
Not for us. Yeah.
So such a field would decay on maybe a time scale of 2 gigayears.
Yes.
And so an alternative idea would be that clusters constantly need to be stirred. And one way of stirring them would be through collisions with other clusters, which do occur on a regular basis. And some of them had a recent merger very long ago, and those may be then the case the galaxies which don't have much magnetic fields. What do you think of that?
Well, in fact, the merger, the stirring will make the field.
Yeah, right. And the absence of it will
Lead to the field decay, but it's quite possible that the synchrotron emitting electrons decay faster than the power law decay of the field.
Oh no, they decay
and also we found
very
that
fast.
the rotation measure decays slower, because when the field decays, whatever Niels and myself there.
The length scale
The length
increases.
scale increases.
Yeah, right.
So the field decays as a power law, the length scale increases, and the rotation measure decays even slower.
Yes.
But synchrotron emitting electron at that observed frequency may go down faster,
But still, it's indeed true what Axel says. If we do accept that most of the magnetic field is produced as a merger event, then there should be an anti-correlation between the length. The longer is the time after the last merger event, the weaker magnetic field you should expect. This has to be checked. But we should talk about this probably to Luigino Ferretti, who has now most observations of galaxy clusters. And they are quite smart there in Bologna. I would think that if one can make such an analysis, they would definitely do it. We still have data for probably maybe a couple of dozens of clusters, detailed data.
and also you have to know the
I don't know.
signature
We
of
should talk to
mergers.
Luigino about that.
Yeah, also you have to know what is the signature of merger. Because in the X-ray you won't see much. You have to see it somewhere else.
This is true, but still, at least this should be attempted. With your best knowledge of the time of the last merger, and with your best knowledge of magnetic field strength, plot one against the other to see if there is any correlation or anti-correlation. If not, you're in trouble. If yes, you publish a new paper. It definitely should be done.
I mean, I think the only thing which can be said for what Alvar says, I'm still trying to defend him, is that seeing synchrotron emission requires two things. Seeing rotation measure requires only one thing. That is, you need
Also two, but one of them is observed to be there, definitely observed to be there.
no, thermal gas is always there. You need to accelerate particles to see the synchrotron emission. And that itself, there are many different theories of acceleration. There can be turbulent acceleration, there can be acceleration in the shocks in the outskirts, there can be some hadronic processes.
But they all have difficulties, right? None of them is as acceptable as, for example, fluctuation dynamo theory, which tells you that definitely there will be magnetic field.
Yes, so there is an asymmetry between these two. It's easier, I think, to get the magnetic energy than the energy associated with it.
Reduced particles. This is just to intimidate you. This is the plan of the next lecture. Just to frighten you and drive you away from the lecture room.
This can't be everything, right? Various clusters.
The fourth. Part 4. All the parts are numbered, come. This is part 3. There will be part 4 galaxy clusters.
Oh, okay, that's your fifth lecture.
Hmm?
Yeah.
So, Axel,
Yeah,
I hope
please.
I will have additional lecture, right?
Yes.
Finished, because
So
otherwise
there's a
I'm not
question,
feeling
yeah.
it before. Yes, please.
We were thinking about the segregation between magnetic field and plasma and gas in the arms of the galaxies. But what if we think the other way around? What if we think that if you have initially a disk rotating with turbulent gas, and what we see is that after some time, if time was no problem, after some time what we see is that we have segregated regions where you have strong magnetic field and you have turbulence. So couldn't it be the fact that after rotating for 110 to the power 10 years, you could have, like, since the intensity of the magnetic field lines are increasing due to the stretching, the density inside those regions is diminishing, right?
No, you mean within the arms, where you have...
Yeah, within the arms.
Okay.
No, but I mean, if you imagine an uniform structure at the beginning, a uniform disk, then the places where the magnetic field would be, segregated in, would not it be a possible solution for the creation of the arc themselves? Like the magnetic field can help create structure in the galaxies?
Yes, but then I would expect arms where magnetic field is concentrated.
No, because since magnetic field intensity implies a decrease in intensity.
You're talking about the pressure balance. Where magnetic pressure is higher, magnetic field is stronger, there will be less gas.
Then you would put the gas outside the areas of magnetic field, right? And wouldn't that
Agreed.
be happy?
Agreed. And this would be fine if magnetic field was not frozen into the gas. Because the gas rotates differentially, and the spiral arms rotate as a solid body.
But
So magnetic field, that if this is true, this means that both magnetic field and the spiral arms must rotate as solid body. Magnetic field rotates as a solid body, and gas rotates differentially. Magnetic field isn't frozen into the gas. Otherwise, they should rotate together. Whatever you do, it cannot be frozen into the gas. I agree with you. The only way to explain this picture is that both the spiral arms are waves, density waves, and then magnetic arms must also be waves. These must be magnetic waves. And I should say that none of the solutions of dynamo equations that thin disk known to me produces waves. Unlike the sun, the case of the sun, where the dynamo waves are readily obtained from a special. Thin disk dynamos don't have wave-like solutions. So it is a problem also for the dynamo theory to explain this part. But what I want to say first, before we start discussing that problem, is that this is clear evidence that magnetic field cannot be frozen to the gas. No way. No way to explain this picture assuming that the field is frozen into the gas. If it is not frozen, it must be made.
Isn't there any degree of frozenability?
Yes, yes. It is called the ratio of you take the ratio of the diffusion time, magnetic diffusion time, to a time scale of the problem. This will be the degree of freezability. If the diffusion time goes to infinity, it's perfectly frozen. If it goes to zero, it's perfectly unfrozen. So yes, you can introduce dimensionless quantity, which will characterize how well the field is frozen to the gas. The ratio of time.
So how do you know that a frozen globe is violated by, say, the turbulence is created by dynamo, not from some plasma instability? There could be some plasma instability that drives the turbulence.
No, but here in these galaxies, I don't need to involve plasma instability. Just see the supernova explosions. We just cannot avoid driving random modes.
Yeah, because you are driving turbulence with that supernova. But in principle, you can have turbulence even without supernova, right? Invoking some...
Theoretically, yes, but if I look into plasma effects, they will necessarily have very small length scales. The plasma turbulence, the plasma effects in the interstellar medium, it produces turbulence at the scales of, I think, astronomical units, 10 to the 15th parsecs. Meanwhile, the random motions observed have the scale of tenths of parsecs. So, significant difference. I don't think there are any plasma effects which can produce turbulence at those scales. There are, for example, various waves, like gravitational waves, which can contribute, but probably not strongly in galaxies.
Stellar wind would also
Oh, yeah.
to the steering.
Yes, they will contribute significantly. So, supernova explosions and stellar winds are the main source. And having such a fantastic source just in front of you, these explosions are readily observable. So, there is no doubt that they will drive. Moreover, for magnetic field, we don't need turbulence as such, right? We just need a random flow. I don't even care whether it will have extended spectrum or not, in many cases. It's only important, sufficient for me to know there is a random flow.
So you mentioned that scientists are doing simulation collision simulation, right? What do you expect from this simulation? And can you comment on the
Well,
ability? I mean, these are very large scale.
yeah.
Looking at the code on
The mean free path with these clusters of particles, Coulomb, with the Coulomb collisions, is 5 kiloparsecs. It's almost exactly the scale of interest. So, but then the standard approach to such problems is to say that in magnetized plasma, the role of the mean free path is played is played by the Larmor radius. Because if there's magnetic field, particles never move along the straight line. They start gyrating. And then the Larmor radius becomes an effective mean free path. Basically, this is the theory, it's sort of an interpretation of a theory developed in the early 60s by Braginsky, Stanislav Braginsky, who also contributed so much to geomagnetic fields. His name, Chris was mentioning his name several times. He's the same Braginsky. By the way, there was a coincidence. His father, Braginsky, was the supervisor of the PhD thesis of my father. Roughly strange coincidence. Well, and there, generally, so the general conclusion of this theory is that indeed you can apply MHD equations. What he does, he takes kinetic theory of such collisionist plasma and then averages. This is how you derive hydrodynamic theory for plasma. You take kinetic equations, average, and so the statement simplified is the following. If the plasma is collisionless, but magnetized, you can introduce effective transport coefficients using the Larmor radius instead of mean free path. But there is a price to pay for it. For example, pressure becomes anisotropic. Pressure along magnetic field and cross magnetic field will be different. So instead of just grad P, you have a whole tensorial structure there. And God knows what else will be there. You know, this is the most outstanding new element. And honestly, I was always just afraid of touching that kind of words. It's Pandora's box. Therefore, I feel that my knowledge of plasma physics is too poor to do something serious there. But Alex Shivachikin, he's very clever, and he works in exactly that direction, trying to look into dynamo action in using MHD descriptions in collisionless plasmas, using various averaging of kinetic equations. Well, God help him. I hope he will really achieve something interesting. But this is, I remember we had with Axel, once we had a postdoc when I just came to Newcastle, who started, the idea was that he will work on clusters of galaxies. But he was a very skeptical and very independent person. He came and said, well, this is what MHD, you are pushing me towards solving induction equation. But it's collisionless plasma. Then we started waving our hands and saying roughly the same words that I said now. This would never convince him. He never made any progress in this direction. Just because he couldn't overcome himself, couldn't apply MHD equations to collisionless plasma. And I understand him. There is reason in this position. So we are taking risk. But those who never take any risk, they never drink champagne.
No, actually, MHD works in the collision plasma. So
yeah, but not in exactly the same equations. Then make pressure, and anisotropic, then do something else. So I'm taking huge risk applying the standard dynamo models to classes of galaxies. It's huge risk. But I think large but justified, not unjustified risk. Thank you.
Thanks, Anwar. So I remind you, we have group sessions again. Very similarly to the first, this should say 2 here. Similar to the first session, we have again 4 sessions, but this time Piali will be in one of the groups. And the method of swapping will be slightly different and indeed more convenient. So the idea of swapping is that after half an hour, Karl lines will move from this to this, and ANWA will move from here to here. So they will simply just swap pairwise, and also these will swap pairwise. And then, of course, after that, there will be a swap between similar auditoria. So the big one in 13 swaps with the big one in 12. And the small one in 12 swaps with the small one in 13. So that's also easy to remember. Any questions?
Which one is 12 and which one is
12 is where the astrophysics group is, and 13 is where the node domain building is.
Don't wait, because somebody will ask where is some detail. If you wait more, somebody will definitely ask.
Where's the copy then? Does anybody know where the copy is?
Yeah.
Let's look for the copy then. Thank you.